last time we understood all of SL2. So we understood UQ of LSL2. And we knew that any irreducible representation was a tensor product of evaluation representations with some suitable conditions. So that's that such a result is not known outside, such a complete result is not known outside SL2. And this is this is for a variety of reasons. So let's make a definition. So now we're working for arbitrary UQ of LG. And we'll say a representation is prime if it is not isomorphic to a tensor product of representations. So an exercise you should be able to do is that for SL2, these representations loops into SL2, UQ, EV star Vn is prime. So I made a comment at the start, at some point when I was reviewing finite dimensional representation theory, which should be enough to tell you why this is a prime representation. Okay? And more generally, for even for SLN plus 1, where we have the evaluation, the evaluation representations are prime. And the remark I'm referring to that you need to use is that V lambda tensor V mu is not irreducible for UQG or UG. So use if lambda and mu are both different from 0. Okay, that's the relevant exercise. Okay, so if we wanted to achieve our goal, of understanding irreducible finite dimensional representations, what do we need to do? Well, what have we understood by the word understanding a representation? Is there a question?
What does that use?
So for this exercise, hint.
Oh.
So to achieve our goal of understanding irreducible finite dimensional representations, what have we learned so far then? So we must, if you look through the analysis of SL2, you have to understand, determine the Drinfeld polynomials such that V pi is prime. The second condition would be when is a tensor product of two prime representations irreducible? If pi and pi prime are prime. It's enough to understand this pairwise. I don't have to understand an arbitrary tensor product. And this is because now of this result of Hernandez, which says if it's pairwise irreducible, then the whole thing is irreducible. Okay? So it's enough to understand B. Then you'd want to understand their Q characters. And you'd want to understand their UQG characters. And we're miles away from doing anything like this, okay, in this level of generality. This is so. So we're very far from achieving the goal. So let me tell you what some examples of prime representations. So just to show you how few examples are even known. So the first one is what I like to call the fundamental representations. So we will see classical analogues of all this, which is why I want to spend some time doing this. So what do I mean by a fundamental representation? So what do I mean by a fundamental representation of G? Right? I mean a collection of non-negative integers, all of which are 0 except one of them, which is 1, right? Lambda equal to omega I. So what do I mean by a fundamental representation of UQ of LG? So what are the irreducible representations given by? They're given by Drinfeld polynomials, right? So what is the analog of wanting everything to be 0 except one thing? That's saying that all these polynomials have degree 0. Since they have constant term 1, they're actually the polynomial 1. Okay? So we say that pi is fundamental if pi j is equal to 1 for all j different from I. And what is the analog of saying that I want that ith thing to be 1? It's saying that I want the polynomial to have degree 1, right? So what does a degree 1 polynomial look like? It looks like 1 minus AU, where A, let's say, is in C star, or it could be in CQ star, depending on where I'm working over the complex numbers of the field of rational functions. Okay? So if you notice then, the fundamental representation doesn't just depend on I, it also depends on this extra parameter A. Okay, so but this A can be gotten rid of. So in fact, this is called, such an n-tuple is called the ith fundamental representation with parameter A. Okay. So let's call this n-tuple, and we'll denote this n-tuple by pi I A. Okay. So let's answer these questions. Let's see which of these questions I can answer. Well, so here's an exercise, which again you should be. I mean, there is, broadly speaking, all the material that you need to do this exercise. V pi A is prime. So how would you sort of try to prove this exercise? So if it's not prime, it's a tensor product of two things, correct? So let's supposing it's isomorphic to V pi tensor V pi prime. right? Now what did I say last time? Such a tensor product is necessarily isomorphic to v pi prime, right? So so that means pi ia must be equal to pi prime, right? Yeah? But this can't happen because the only non-constant entry at degree 1. Right? So it's prime. The answer to this is known. So this is known through the work of many people for fundamental representation. So it's known through the work of Varagnolo. Maybe it should have been the other way. Vasaro. Kashiwara. And I wrote a paper on that some time back, and so on. Okay? So the answer to this is known. The Q characters are known. This is again through the work of many people. It goes back to Frenkel and Reshetkin in the non-exceptional cases. And then there are combinatorial algorithms by Nakanishi. I had some work with Mura, which has a slightly more Lie-theoretic flavor. And Hernandez, and lots of people have worked on this. Okay. And the UQG characters are also known, and in this case it can be deduced from the Q characters, but they were known before in work that I did with Presley. So for fundamental representations, things are pretty well understood. So they are prime for a very simple reason, and you know their Q characters and so on. Yeah.
What did you say about question B?
When is V? So this is known through the work of many people.
For the fundamental representation.
Yeah.
So if both pi and pi prime are.
Yes, I am working in, yeah.
So if pi and pi prime are fundamental,
Yeah.
that's the question.
Yeah, pi and pi prime fundamental. Right. Okay. So in fact, a very important consequence of B, this question that you raised, which is again going to be relevant for us, is the following. So a consequence of B is the following. Supposing I take pi as an arbitrary set of collection of Drinfeld polynomials. Okay. Then V pi is a quotient of a suitable tensor product of fundamental representations. Okay. So let me give you an example to show you how this works. Okay. So supposing I'm working with an algebra of rank 2. Okay. Rank of G is equal to 2. Yeah. And let me take a very simple, let me take something like this. 1 minus u into, let's say, 1 minus au. That's my first Drinfeld polynomial. And my second Drinfeld polynomial is this. Okay? Then what this result says is that, so how can I factorize this into a product of fundamental representations? Right? So I could write this as pi 1, 1. So what is this? This is pi 1, 1, and then this is pi 1 a inverse in that pi 1 a in that language, and pi 2 b. Do you agree with that? Yeah. This will look like 1 minus u1. This will look like 1 minus au1, and this will look like 1 minus bu. So if I multiply this up, right, I'm going to get exactly pi. Right? And so what this result says is I can take the tensor product of these things in some order so that it's cyclic and v pi is a quotient of them. So there exists an ordered tensor product. So let's just assume that I first take this, this, and this, such that such that the tensor product of the fundamental representations is cyclic and hence a quotient, and hence has V pi as a quotient. Okay. And so in fact the theorem, which is far from obvious, is that the local Weil module that I defined, W pi, is exactly isomorphic to this tensor product. To this tensor product. So, yeah. So this tells me when a tensor product like this is irreducible. Okay. So from this, actually, I also know when it's cyclic. When I'm proving this theorem, I also know when this tensor product is cyclic or the tensor product of highest weight vectors. Okay. So a consequence of that result is that V pi is a quotient of a tensor product of fundamental representations.
So you're not proving this?
I'm not proving this. I'm just trying to explain what a consequence of that is. And I'm trying to explain how you might get it.
So for any V pi?
Yeah.
Any V pi, so there exists some order.
Exactly.
And if
Yeah. And then I'm saying that it doesn't matter, in fact, as long as the ordering is such that the tensor product is cyclic, what you get is this local Weil module, which are defined entirely through generators and relations. And which is also given by Nakajima, and it's called the standard module. So that is the theorem. Most of the time, if these things are sufficiently generic, then this tensor product will be irreducible. It's when they differ by powers of q that you have to fuss about it. Okay? Yeah, I'm not proving this, I'm just saying it's a consequence and that it. So this relates to the question that you asked me the other day about what is the dimension of this Weil module, which I said was 2 to the n, right, for SL2. So let me explain how that comes out of this. So supposing we do SL2. So supposing we do SL2, and we have, then in that case we have a single polynomial, Rindfeld polynomial, pi, right? And let's assume that degree pi is n. Right? Then I can write pi as 1 minus a1u into 1 minus a2u into 1 minus a(n)u, right? I'm just factorizing it. What does this theorem tell me? I can choose an order on a1, a2, an, such that, so we can choose an order, and let's assume I've chosen it. Such that W pi is isomorphic to V1 minus a1u, sorry, right, into tensor V1 minus a(n)u. Right? It's a tensor product of irreducible representations associated with each of these polynomials of degree 1. Okay? So now, I told you what anything like this looked like. This was just isomorphic to C2 as a vector space. So if you look through your notes, if you had a polynomial of degree 1, the associated representation was exactly the natural representation of SL2. So this is a polynomial. So what is the total dimension over here? The total dimension is 2 to the n. Yeah? Now if I took pi to be that very special polynomial that I had last time, right, where the roots differed by a string, what is the dimension of that? That was n plus 1. Okay. So if pi equals, so the dimension of W pi then is always equal to 2 to the degree pi for SL2. I'm still in SL2. If pi equal to pi n a, So this was the polynomial 1 minus aq to the n minus 1u into 1 minus aq to the minus n minus 3u, and so on. Then the dimension of v pi, on the other hand, which was exactly equal to n plus 1. So v pi is minute when compared with w pi. Okay, and it's for this reason. Okay.
Can we somewhat more basic questions?
Yeah.
You had mentioned that v pi tensor v pi prime product for the thing without the q, right? Because you said something about co-multiplication only being group-like for up to first order.
That's right. But even then, so what you can still prove is that it behaves well enough for that to happen.
So that's
You can control, yeah, exactly.
in the q case.
Yeah. So you can control it well enough for that. Yeah. Yeah. So that remains true in the Q case. Yeah. Okay. So can I go on? Yeah. Okay. So there's another family. So there is a generalization of this family of modules, and these are called the Kirillov-Reshetikhin modules. Yeah. I'm just giving. This theorem is for arbitrary simple Lie algebras. But this illustration. Okay. This is true for arbitrary UQLG. Okay, so what are the Kirillov-Reshetikhin modules? They're sort of what very often when you're doing when you're doing Lie algebras, you understand the fundamental representation, and then you understand multiples of the fundamental representations, right? The so-called rectangular weight, right? So you do this. So Kirillov-Reshetikhin modules. These are analogs of n omega I. Where n is bad notation, so let's call it L omega I, where L is an arbitrary positive integer, non-negative integer, and 1 less than or equal to I less than or equal to n. And how do we generalize them? You take 1 in every place, the Drinfeld polynomial 1 in every place. I'll tell you, in the ith place, I'll tell you what to write, and then 1 again. Okay? And over here, what do I want to write? I want to write the polynomial pi L1. And pi L1, I've defined for you here. I'm taking n to be L, a to be 1. So it's easier to perhaps just write it again. So pi L1 equal to 1 minus q to the L minus 1u into 1 minus q to the minus L plus 1u. Okay? So if you take these, the modules associated to these are called Kirillov-Reshetikhin modules. The irreducible modules associated to these okay. So again, it's a slightly harder exercise, but it's still an exercise. The Kirillov-Reshetikhin modules are prime. And and there's extensive literature on these modules, and through the work of many, many people, one knows everything about these modules. And what do I mean by everything? One knows that I've told you that Drinfeld polynomials, but you know their Q characters, G characters, you name it, you know it. In the sense of what I described as my goal. You know when the tensor product is irreducible, you know that tensor products are always irreducible. So life is really good for these kinds of modules. They're important, very important for another reason. Kashiwara's conjecture is these are the only, these together with the tensor products are the only modules with a crystal basis. So through the work of Ocado and Schilling and Shimazono and so on, you know that Kirillov-Reshetikhin modules have a crystal basis. Therefore, the tensor products of them have, but the only is not yet known. Okay. So
what do you mean by crystal basis?
Well, you're not serious, right? Kashiwara has an elaborate theory of crystal bases. So there's some kind of canonical basis, if you prefer. So there is a nice basis which behaves well with respect. So the analog of this crystal basis would be the canonical basis of Lustig.
So the UQLG itself does not.
It has a canonical basis.
UQLG also does.
All this canonical basis stuff is adapted to this other triangular decomposition. So the highest weight modules in the sense of cats have canonical basis. But they're not so nicely adapted to these finite dimensional representations. Okay. So it's known that Kirillov-Reshetikhin modules have crystal basis or canonical basis. So only a part of Kashiwara's conjecture is still known. So what one needs to know is it true that no other prime representation has a crystal basis? So this is certainly not known. The reason you have to put in the word prime is otherwise this is not a well-formulated question, because tensor products of things with crystal bases have crystal bases. So I have to exclude those. So, okay. Okay, so now let's look at these Kirillov-Reshetikhin. So there's one or two more things that I want to say. Let's look at these Kirillov-Reshetikhin modules. These are analogs of L omega I in some sense, natural analogs of L omega I. So then what is the next obvious question to ask? Why specialize to n omega I? Can you somehow define some special family of modules associated with any dominant integral weight, right? So generalization of, so these generalized Kirillov-Reshetikhin modules, so what one would mean is associated to any dominant integral weight. So these also exist in the literature. So these were but these are actually called minimal affinizations.
So this last module is associated with the term.
Sorry, say that again?
Is this your definition of Kirillov-Reshetikhin?
Yeah. The modules associated to such are called that. Yeah. So now I want minimal affinizations. So they're not actually called generalized Kirillov-Reshetikhin modules in the literature because these were sort of defined before Kirillov-Reshetikhin modules became terribly popular. And so these were defined by me and then studied further in work with Presley. And what we were motivated by was perhaps the following more elementary question, which is, okay, so you don't have evaluation representations. Is there some smallest representation of UQG, not necessarily irreducible, which you can make into a UQG LG module? Okay, so we're looking for the smallest representation of UQG, depending on lambda, which can be made into a module for UQLG. Okay, so this is a very imprecise statement, but actually it's sort of motivated by these notions of K-types, which appear in the representation theory of semi-simple Lie groups, for instance, in Harish Chandra's work. So minimal K-types. So what does that mean? So I have V. So I'll stick with my situation, but it should be familiar to people who do that. So if I take V, it's a UQLG module. So I can write V as being equal to direct sum V mu with mu in P plus, right? And maybe with some multiplicity. This is just, so this is like if you're taking a complex, a semi-simple Lie group, for instance, and you regard it as a representation for the compact portion, you can write that as a direct sum of these things, right? And then, what do you want to say? You say that, so you say that V is an affinization of lambda if what? The following happens. If m lambda is 1, this actually depends on V. So if m lambda V is 1, and m mu V is 0 if mu is bigger than lambda. And then, so there are many such modules with this property. You say that V is minimal if the following happens. If given any other affinization of lambda, we have for all mu in P plus, the following must hold. Either m mu V is less than or equal to m mu W, let's say less than m mu W, or they're equal, but this happened earlier. So this is a bit head spinning, but it's actually not so difficult once. This is very similar to things that you see in the representation in Vaughan's theory of GK pairs, for instance. It's either, so the multiplicities are either equal, it's got to be less, and if it wasn't less, it's because if it isn't less, it's equal, and it had become smaller earlier. Let me give you an example of this. Let's work with SL2. Yeah. So we have our favorite representation. So I'm going to take a small example. I'm going to take pi 2a, which is 1 minus aq into 1 minus aq inverse. Okay. And then I'm going to take another example, which will be, let's say, 1 minus a into 1 minus aq cubed. Yeah.
Is nu less than mu?
Nu in P plus and nu bigger than mu. Nu is bigger than mu. Mm-hmm. You don't have, yeah. It happened earlier. By earlier, it means higher. Yeah. Okay. Yeah, I mean, there is no way to motivate this definition except that I've seen this definition in other contexts in representation theory. And so it was just an attempt to see if it looked like that. Okay? But let's look at this example and see how this fits. What is the irreducible representation associated to this? Okay, as an SL2 module, the irreducible representation associated to this is exactly V2 as SL2 modules. This is what I told you yesterday. And now if you look at this tensor product, if you look at this doesn't satisfy our favorite condition, and so the module associated to this is V1 tensor V1. Okay, so this is an exercise you should be able to do because I told you what the reducibility conditions are for tensor products. Okay, so it's this. So I claim that V pi is greater than or equal to V2. Because, well, what do I have to check? 2 occurs with multiplicity 1 in both places. I'm not worried about that, right? And mu different from lambda. Because those will always occur with multiplicity 1. Okay? And there's nothing else I have to check over here, right? I have something over here, but I don't have to check that it's bigger. There's nothing else to be checked. There is no, every other multiplicity here is 0, right? And over here I have multiplicity 2 and the trivial. Okay? So in fact, in the case of SL2, one can write down exactly what all the classes are. So it's what this partial order can be written down. This is a partial order. I'm not saying that this is a minimum. I'm trying to check that V2 is less than or equal to V pi, right? I'm trying to analyze this condition. So over here, what do I have? I have M2 of V2 is 1, right? Or M2 of 2, as it were, is 1. No, M2 of V2 is 1, and Mn of V2 is 0, if n is different from 2. Yeah? And I have over here, the highest weight is 2, which occurs with multiplicity 1, and 0 is less than or equal to anything else which might appear over there. This condition is... I never have to go to part 2 because part 1 is holding. Mu nu is always less than, mu v is always less than mu w.
Because for the other one, this is positive.
Something is positive, so they both, the highest weight is 1, occurs with multiplicity 1, which is allowed. There is no other highest weight in this module. So everything else is 0. And the only what occurs here is either 0 or 1. So this
No, but the second condition sort of reads that they should be higher and higher and higher.
yeah, so I'm not saying this correctly, am I? So 0. I mean, I only want this condition if this is greater than 0. I don't want it to be higher and higher. I mean, what I want to say is that if it occurs with some non-zero multiplicity, and the 2 multiplicities happen to, I mean, these conditions are only going to be made for non-zero multiplicity. Right? I don't want it to grow randomly. So, yep. So either this happens, or, so let's have less than, or m mu v equal to m mu w is greater than 0. Then this happened earlier. So, so this is perhaps not the most interesting example, but one can. I have to, yeah. The sizes of the examples become too big otherwise. Okay, so this is called a minimal affinization. So minimal affinization. So the work that Andrew and I did was we wrote down Drinfeld polynomials for minimal affinizations, but we couldn't do it in all generality. So we did it for algebras of type A, B, C, F4 and G2. And for algebras of type D and E, the classification is, we couldn't complete it quite. And the reason for that is these two algebras have a trivalent node. There's a node which is connected to 3 other simple nodes, and that is always problematic. So we couldn't finish it in that. I think Mura very recently, so we did this work in the 90s, and Mura very recently did D4, which I think he talked about last year. And then, so whenever the classification is available, Hernandez wrote down Q characters. And there are some very partial results on that structure. There are some conjectures which I made with Greenstein, and then there's some work of some Japanese. So very partial work on that G module structures. But of course, all results are increasingly partial because they all depend on this classification, which is not complete. Okay. So it's very hard to. So what happens is that what we could prove is that there's a unique minimal element in the case, essentially, in these cases. But when you go to these cases, the minimal elements are no longer unique, and and when it's supported on the trivalent node, it grows randomly with lambda. So that's really very difficult to do that. Okay. So these are all the interesting families of modules for which things, yeah.
So this, this minimal affinization is irreducible
By definition.
by that.
Oh, yeah. So you work with amongst the irreducible representations associated to lambda. So any irreducible representation associated to lambda has these properties, that the top thing occurs with multiplicity 1, and all the other things are below it, in the cone below it. And then you you look for it all the time.
So the definition of affinization, you are assuming that it was an irreducible representation to start with.
That's right, yeah. I mean, you don't have to put it in, but when you want to classify irreducibles, then you restrict yourself to looking at irreducible things, okay? So I've told you about Q characters and G characters of these minimal affinizations, and so what I haven't told you, so Hernandez and I believe that minimal affinizations are prime. He would say we have a proof, I would argue, but most likely minimal affinizations are prime. Okay, so this is sort of, I don't know what to call it, discussions with Hernandez, because it's.
So this, you prove so the existence itself is a question, right? You have to prove the existence.
Yeah, proving the existence of, so that is not quite so difficult. Because of this tensor product kinds of results, that they all occur there, and then there are only finitely many multiplicities that are possible. So if you look at that set, it's somehow well behaved. So I'm not being entirely precise in many of these things, but yeah, existence is not difficult, but how many there are, that requires work. How many minimal elements there are with respect to this partial order. I should also tell you, when you define this partial order, you can talk about maximal elements as well. And through all the stuff of wild modules that I was talking about, the maximal elements are wild modules. So there's a unique.
Maximal irreducible.
Yeah. No, it's not, wild modules need not be irreducible.
I mean,
Yeah, something like.
but you could always add another bigger one.
No. So if you retain this condition, m lambda v equal to that, 1 and mu v equal to 0, and you look over that, and the maximal thing is the wild module. You can look just among cyclic modules, right? So, and define this notion. So it's a question of where you want to define your partial order and where you want to look at it. So, so there is a unique maximal element, but lots of minimal elements, in principle. And I mean, really, but when we found out for D that number of minimal elements increases with lambda, we gave that up as a bad job. But anyway, at that point it wasn't clear that it tied in with anything else. So, but now with this recent work of Hernandez and so on, it's more interesting because you can do Q characters. So anyway, so the two other ideas is probably minimal affinizations are prime. So this, my answer to this is maybe. Tensor products of minimal affinizations, very little is known about them. Again, outside, so there are some, this is somewhat studied in SLN plus 1, but no general answer because, oh, no, right, so let me correct myself. Tensor product of minimal affinizations. So for SLN plus 1, this is, again, the minimal affinizations are just evaluations. So remember, I'm looking, when I defined these minimal affinizations, I was looking for generalizations of evaluations. So where there is an evaluation representation, it is the minimal affinization. And tensor product theorems are known through the work of Nazarov and Molev, but I don't think their answers are complete. I mean, so there isn't a result which says that the tensor product of two evaluations is irreducible if and only if something happens. People usually give necessary conditions or something like that. So at this point, I think I've said what I want to, so I will stop now and then we can go to the somewhat more classical case after the break. Okay, so now I have to say two more things about why I can reduce myself to the current algebra, which I'll do now. So I've said many times that if you take V to be a UQLG module under some, in fact, V pi, then you can put Q equal, sometimes you can put Q equal to 1. In which case, and get an LG module. So I made some comments of when we could put Q equal to 1. So for instance, if you're doing V pi, and pi lives in Z cube Q inverse U, then limit Q going to 1, V pi exists. Exists, and we have, and okay, and so we get and give an indecomposable finite dimensional module for LG. And there is another critical thing. So many of these examples of modules, like these Kirillov-Reshetikhin, so that's why I've been telling you about them, Kirillov-Reshetikhin, minimal affinizations, and so on. Specialized, so I can put Q equal, have Q equal to 1 limit. But they also have another very important property. They're actually modules for the following quotient. So for G tensor CTT inverse, modulo T minus 1 power R. Minimal, while, all of them. For some R. So what that means is, so this is something we've seen. Supposing I have a finite dimensional module for LG, right? We saw that kernel of rho is an ideal of finite codimension. Right? And that means that rho is actually a representation of G tensor CTT inverse modulo some ideal I, right? We've been discussing this a lot, right? Now what does this ideal I look like? We're in a principal ideal domain, so this is just a product of powers of maximal ideals, right? Power given by points. And so, what am I saying over there? When I take all these nice families of special modules, okay, in fact very often they concentrated at a single point, at t minus 1. The ideal, the kernel, is actually just generated by t minus 1. Let's try saying that again, or is that? Is it easy to see that the limit is indecomposable? Yes, because these modules are all generated by a cyclic vector, right? You have your little v pi. So when you take your lattice, right? What is this generated by? It's generated by the element v pi tensor 1. Right? So, and then what happens to, and then this is and then this element you'll see is generated by this. I mean, will satisfy these relations. Then Poincare-Berkowitz theorem, this will have a unique irreducible quotient, so it'll be indecomposable. The top weight space will continue to be one-dimensional and will be generated by its top weight space. So yes. So the proof, imagine the proof that you would give for the characteristic P module being indecomposable. It's the exact same proof. Okay, so what I'm saying over here is, so for most interesting examples from quantum affine algebras, so for most interesting examples coming from UQLG, we can take Q to be, I to be t minus 1. Okay. T minus a power of t minus 1. The ideal generated by that. Okay, and what is the fact? I mean, we've always had these current algebras lurking in the background. What is the other fact? If you look at G tensor CTT inverse by I, well, this is quite clearly isomorphic to G tensor CT by I, right? Here, well, if you like, I plus. Here you take I to be the ideal over here, generated by t minus 1. Here you take I to be the ideal in CT, generated by t minus 1. This is a simple exercise, which means I can then, now I'm down to a representation of the current algebra, and then I'll just shift t by t minus 1, and then I can work with the, which you can think of as isomorphic to G tensor CT by t power r. And here, how are these two isomorphic? This is given by t going to t plus 1 or t minus 1 or something like that. The automorphism of that. So I can shift. Okay? So ultimately, this is why I was interested in representations of the current. Or at least, if somebody asked me why do I care, this is why I would care. But it turns out that anyway, it's entertained me for a while, so that's good enough. Okay, so this is my final justification for studying representations of the current algebra. And not just any, I'm really going to be sort of on a particular category. So why did I do the shift? What this shift allows me to do, CT is naturally graded by the integers, right? And here what I'm doing is I'm taking a graded ideal. That's why I wanted to go from here to here. And so what and the further justification for being allowed to do that is that when I did my Kirillov-Reshetikhin modules and all these nice modules, somehow you can see that they come equipped with some grading. It's hard to explain why, but they do. And they actually you can think of these actually as modules for this algebra. Okay? So let me now, so from now on we'll write GT. So now I'm going to talk about the current algebra and its representations. And so now for the rest of this lecture, I'm not going to sort of give an overview of things. I'm just going to start doing things. And I think there's been enough time spent on explaining motivation and so on. So I want to now tell you exactly what setting we're going to be working in. So GT is going to be my Lie algebra G tensor CT. And it'll have our favorite commutator. So this is X bracket Y tensor FG. Okay. The category I'm now interested in is G. One of the many categories still that we'll be interested in. This is going to be the category. No. So before I define this, I have to tell you about grading. So GT is a graded Lie algebra. So what that means is it's a direct sum. So quite clearly it's equal to the direct sum over R in Z plus, G tensor T power R. Right? And if you take, what do we mean by graded Lie algebra? You take graded components, take their commutator, they lie in the sum. Right? So G tensor T power R, bracket G tensor T power S, is quite clearly contained in G tensor T power R plus S. Okay? So it's a Z plus graded Lie algebra, in fact. And this fact that we can think of it as Z plus is very important because somehow, I mean, the loop algebra is also graded, but it has grades going in both directions, and that really messes you up. So this is better. Okay. Then U of GT acquires a natural grading as well. What is the grading here? Well, what does the basis for U of GT look like? You just take products of monomials, right? And then each element in that monomial is graded, so naturally. Okay. So the category G will be the category of Z-graded modules. So now I really do want Z and not Z plus. And I've lived in the US for too long. It took me forever to learn to say Z, and now I'm where I should be saying Z. So it's the category of Z-graded modules for GT. And the morphisms in this category, so each graded piece is a sum of finite dimensional G modules. We're making this a restriction. So that means an object in this category will be V equal to direct sum VR with R and Z, right? If it's to be a graded module, you must have that G tensor T power S acting on VR is contained in VR plus S, right? And if I take S equal to 0, right, then VR is a G module. Yeah? And I'm demanding that it not be a random G module, but that it be a sum of finite dimensional G modules. Okay? So the objects in this category can be very large. I'm not demanding any kind of finite dimensionality or anything, because if I do, then I can't do any homological algebra, because I don't find projectives and things like that very easily. Okay, so I want this to be a very big category. And the morphisms, so the morphisms in the category, so a map from V to W, so this must be a map of GT modules, and it must preserve the graded pieces, so they're degree 0 maps. Okay. Okay, so this is our G. So what are our simple modules in this category? How would we write down what the simple module in this category? So supposing V, simple objects. So supposing V is an object of G, and V is simple. What is the standard trick that you play when you work in this thing? So choose R0 in Z such that VR0 is non-zero. You should be able to choose that, otherwise the object was 0, right? And then lemma. Then V is equal to VR0.
The rest is 0.
Exactly. So why is the rest 0? Well, I mean, so you're giving me a construction of an example.
Consider the R naught plus first graded piece.
Yeah. So then that generates. So look at the next grade. So supposing. So you look at. So look at the summation k greater than R0, vk. Yeah. This is clearly a GT submodule, and this is where things begin to go wrong already when you're working with GTT inverse. Okay. But this is clearly a GTT submodule, so this better be 0. And so you can have at most one graded piece, which is non-zero. So you have this lemma. So V is equal to VR0. And since V is simple, GT, this means that it also means that VR0 is a simple G module, right? Because otherwise the G piece itself would have a submodule, and then GT doesn't go in. GT has nowhere to go. So xt power k on V is 0 if k is bigger than 0. This is the implication, right? So this implies is a simple G module. And then what does that mean? That means that VR0 is isomorphic to V lambda for some lambda dominant integral. Yeah? Should I be repeating anything? Is this okay? Yeah. So I've got VR0 equal to V lambda.
Are you assuming here find there's a left bound on the grade?
Why am I assuming that?
No,
No. I don't want to assume that for the moment.
they could go in either
They could go infinitely
way.
You have to say a few more words in that first step.
in this step, right? Yeah, I know.
On the left hand side.
That's right. So so how do we get rid of that? Yeah. Okay, so this shows me that at least I can't go down, right? And then why is it true that everything above is 0? So supposing VR0 minus 1 is non-zero, then I have that VR0 is in a submodule, right? So once Vk is, right? So, okay, yeah, I was cheating. So this tells me that everything bigger than R0 is 0, right? So now I have to tell you why everything less than R0 is also 0. So suppose that Vs is 0, non-zero, for S bigger than R0, less than R0, right? Then I take Vs plus so on, and now this, and then I'll come to Vr plus so on, and this will be a submodule, which also can't have happened. So yeah. Okay, so I don't need this bound, but okay. So then what have I shown? So what I've proved then is that if V is irreducible, object of G, I've proved that there exists lambda in P plus and R in Z such that V is equal to VR, and this is isomorphic to V lambda as a G module, right? So that means a simple object, to give you a simple object, I have to prescribe lambda and R. And how do I go the other way? What should I do? So given lambda R, what do I do? We'll define V lambda R to be the object in G with the following properties. So V lambda R on S will be 0, S not equal to R, and this will be V lambda if S is equal to R. And how does X act? I mean, how will Xt act? In the obvious way. So Xt will act as scalars, as evaluation at 0. So Xt power k on V will be 0 if k is not equal to 0, and otherwise it will be X acting on V. Another reason that you want current algebras, okay? So in other words, simple objects in G are indexed by pairs lambda R in P plus cross Z, and any two such things are clearly non-isomorphic. Right? V lambda is not isomorphic to V mu naught. So this device of insisting on graded, what it has done for me is gotten me into a very discrete situation for parametrizing irreducible modules. Otherwise, my irreducible modules are given by Drinfeld polynomials, which is highly, which is sort of continuous data. It's not a discrete data. And that makes life very difficult to work with, at least for me, because everybody works in a discrete situation. So this device has forced me, so the irreducible objects in this category are given by discrete data. You don't have these continuous parameters showing up, okay? And so one is more hopeful that one can use other techniques to study. Okay. So let's write down what our projective objects are. We can immediately do that. This category has enough projectives. So for that, let me just write down. So supposing, I think I'm going to, so given lambda R in P plus cross Z, we'll define a module P lambda R to be just, you take U of GT, okay? You tensor it up with UG over UG. Let me do lambda 0. V lambda. I'm going to think of V lambda as living in the 0th piece. Okay? And P lambda r will be the graded shift of P lambda 0. So tau r is a grading shift operator. Okay, this is a cheap device. If you have any module in your graded category, you just translate all the grades by r, and you call that. You don't change anything else. You just think of it, the grading as being different, and that's called grade shift. Okay, so that means tau r v s is vr plus s, and the action is unchanged. So you can, this lives in the same category. Okay, so proposition. P lambda r is an object of my category, and it's projective. And P lambda r is indecomposable, and has a unique irreducible quotient. I haven't said that it's projective. P lambda r is indecomposable, projective in G, and has a unique irreducible quotient which will be V lambda r. In other words, P lambda r is the projective cover of V lambda r. Okay? So what do we mean by projective object of a category? It's just a standard notation, a standard thing of projective. So if you have a, so if you have, supposing you have A, B in our category G, and you have a morphism in your category, pi is a morphism, and you say that an object P in object G is projective. If given any morphism here, you have a morphism there. Yeah. So you don't demand that it be projective with respect to all modules, just with the modules that lie in your category. Okay? So that's what projective object is. And the claim is that this is so. Okay? Okay, so I want to prove that this object lies in my category, right? So what are the things I have to prove? I have to prove that it has a Z plus grading. Yeah? Yeah.
Is this the same as taking the adjoint representation in each degree and then tensoring by V lambda? And then,
Right. That's exactly what I'm going to say.
and then sort of, but you're going to have to sort of spill over into the next coordinates as you tensor by V lambda.
Spill over into the next coordinate.
In this, I'm just wondering how you compute this tensor product here over UG. I mean, so you just UG, just UGT as a graded module is just a copy of the adjoint representation in each spot. Right?
Oh no. What about things like x tensor t power r, y tensor t power s?
I'm just talking about U of GT by itself.
Yeah.
Yeah. As a graded module.
Yeah. What about these products? This lives in U of GT.
So what is the component of degree R?
What is the graded component of degree r?
R cube GT.
Okay. So let's do. Supposing let's write this down. So UGT of 0 is 1. No. What is that? That's UG. Right? What is UGT of 1? How will I get elements of grade 1? I have to take all elements of grade 1, but they'll only come from here. And then I have to take everything of grade 0. If I do 2, how can I get them? I can get G tensor T squared, which is the copy of adjoint that you're talking about. But I can also get G tensor T products of the form G tensor T times G tensor T. And then they are UG. So it's a giant module. I mean,
And the effect of tensor by V lambda on that,
yeah,
the component is to do the tensor component-wise.
exactly.
So it's not like the V lambda will sort of multiply one register to the next.
No, it just, yeah, I'm trying to come to what the graded components are. That's roughly what you're asking me, right? So to tell you what the graded components are, these are the graded components of U of GT, and then P lambda R of the graded component. So then we have that P lambda, so we set P lambda, let's write 0 of S to be equal to U of GT S. So you take the Sth component over here, right? You observe that it is a right module for U of G, because if I multiply it by something in U of G, I stay over there. And so then I can take this tensor with V lambda. Yeah? And so P lambda 0 is clearly a direct sum of P lambda 0 S. So at least it has a compatible Z grading. Z plus grading, actually, in this case. And, for it to be an object G, it's not enough to have just this grading. It has to be a direct sum of finite dimensional modules. Each piece has to be a direct sum of finite dimensional modules. Yeah? Well, what did I write over here? So if you look at this, I just need to prove that everything in here is in a finite dimensional graded piece, and that's the adjoint representation being. So the exercise, which I'm certainly too tired to do now, but I could either do it next time or we can discuss it, is that UGT, regarded as a module for G via the adjoint representation, via the adjoint representation is a sum of finite dimensional G modules. So nobody asked me the question, how is P lambda R a GT module? Well, that's obvious by left multiplication. This is just the induced module construction. And here suddenly I've gone to adjoint. Right? I've said that I regard it as a module for G, it's some adjoint module. So why does that happen? That happens roughly because we're working over UG. Okay? So I'll do that a bit more next time. Okay? Or we can do that in discussion today. Okay, so with that I'm going to stop for today. So from now on it's just going to be about this stuff, and I'm going to give as many proofs that you or I have patience for. But this might be fairly limited patience. Okay, so thank you very much.